Okay, so need to start recording and not forget to press the recording button. So I was just saying that a nice illustration of the chain rule is for this thermodynamics problem. So you can take the ideal gas law, which gives you a relation between the pressure and the volume and the temperature for an ideal gas. Here N and K are like constants for our situation. And the point is that you can use the ideal gas law and solve for your favorite variable. So for example, if you want to understand pressure in terms of volume and temperature, you just need to divide both sides of the equation by V and you get this relation. If on the other hand you want to understand temperature as a function of pressure and volume, you just have to divide by NKV and you get this relation. And finally, if you want to understand volume as a function of pressure and temperature, you can just divide by pressure and you get this relation. Okay? So now the question is, as an interesting theoretical exercise, what would the product of these three partial derivatives be equal to? So again, if you just go by the symbolism, right, by the terminology, there's a strong temptation, a very powerful temptation to just say, well, maybe this one will cancel this one, and this one will cancel this one, and this one will cancel that one, and then you say, oh, is this one, maybe? And so this is an example where the notation can lead you astray. And that's why you cannot just do, I mean, there's some, the notation should be useful in the sense that it can allow you to get away with things even without knowing what's going on, but it cannot make miracles. So at some point you need to know what's going on. So, for example, what is the pressure? What is the partial derivative of pressure with respect to temperature? Pressure with respect to temperature will just be this expression. What is the partial derivative of temperature with respect to volume? It will be this expression. And what is the partial derivative of volume with respect to pressure? Well, it will be this thing. So when you do the product of all of them together, right, what do you get? You get this cancels this, one pressure cancels one pressure here, and so you get minus NKVT divided by PV. But if you look, because of the ideal gas law, NKVT is PV, so you get minus PV over PV, and so you get negative 1. Okay, and so really instead of 1 we're getting negative 1, which is sort of surprising. Not what maybe you would have expected if you just go with the notation. The full justification of why this, and this is not just for the particular gas law, this happens in general when you have, like, this is called like Euler's formula. If you have like a relation between three variables being equal to 0, like for example, then you can think of this equation as allowing you to formally solve for one of the variables, like this is some implicit function theorem type idea. And so the point is that what you get is that, say, let me check, PV, okay, yeah. You'll do something like this. But that's the thing. The issue is that you have to be careful when you write something like this, because this means consider x as a function of y and z. Okay, so that means that this partial derivative really, and then this means consider y as a function of x and z, consider z as a function of x and y, and compute the corresponding partial derivatives. And so the thing is, like, when you write x as a function of y and z and so on, the function itself is changing from circumstance to circumstance, right? The function of two variables that you're using in each instance. So sometimes what people will do in order to prevent you from the temptation of differentiating like this is that they will emphasize the variables that you are keeping constant when you're doing the partial derivative. So this notation means think of x as a function of y and z, but just differentiate with respect to y. And this means think of y as a function of z and x, but just differentiate with respect to z. And this one means think of z as a function of x and y, but just differentiate with respect to x. And so this way you cannot really try to cancel things out because they're being protected by this bracket outside each expression. Okay? But if you really want to know what's going on here, you need to sort of understand something that's called differential forms, in case you want to Google it in your free time.